In previous modules, we've been looking at socio-ecological systems from the perspective of feedback loops and resilience. In this video, we'll be taking another perspective on this dynamic between the social and ecological domains as we talk about sustainability. The idea of sustainability offers us another lens with which to understand the complex interaction between society and ecosystem. The rise of the term sustainability over the past few decades has been phenomenal, as it has rapidly gone from the fringes to the center of our collective conscience. This graph showing the number of times the word occurs in a book publication shows a stellar takeoff around the late 80s. In the research literature, sustainability articles also started growing rapidly beginning in the early 1990s and have been doubling every 8 years since. Modeling sustainability through social-natural interaction is an inherently complex process, the analysis of which requires inter- and transdisciplinary efforts. The philosophical and analytical framework of sustainability draws on and connects with many different disciplines and fields. In recent years, this has formed into an area that has come to be called Sustainability Science, which has been described as an emerging field of research dealing with the interaction between natural and social systems, and with how these interactions affect the challenge of sustainability, meeting the needs of present and future generations while substantially reducing poverty and conserving the planet's life support systems. Research relevant to the goals of sustainable development has long been pursued from bases as diverse as geography and geochemistry, ecology and economics, or physics and political science. Increasingly, however, a core sustainability science research program has begun to take shape that transcends the concerns of its foundational disciplines and focuses instead on understanding the complex dynamics that arise from the interaction between human and environmental systems and how they give rise to more or less sustainable outcomes. One of the great challenges to sustainability science today is in trying to develop generic models that capture the essential variables and interactions between society and ecosystem that affect the system's overall sustainability within some overarching framework. Socio-ecological systems are inherently complex assemblages that are spatially heterogeneous and change over time according to an intricate interplay of a large number of biophysical as well as socio-economic factors. Effectively modeling them requires systems-based, holistic approaches that are able to integrate the many different perspectives involved. Sustainability can be defined as the ability to be sustained, supported, or upheld. In more general terms, sustainability is the endurance of a system or process. When we talk about sustainability in the abstract, we're really talking about the state of the system over time. We're talking about how long the system or process can continue at the current level of functionality before it becomes degraded to a lower level of functionality. For a system to be sustainable, or what we might call viable, it has to be consuming at or less than the aggregate level of production to whatever resource is sustaining it. Equally, it has to be able to adapt to its changing environment. So on its most basic level, this question of sustainability is an equation between what is being consumed and what is being produced. But of course, this is a very complex equation when we're talking about a whole economy and supporting ecosystem with many interacting moving parts. So we'll firstly talk about this more concrete side to the equation of sustainability, trying to identify some of the primary variables and key dynamics, before going on to discuss the idea of economic and social adaptation with respect to sustainability. The sustainability of a socio-ecological system is not a simple equation, but it does help to understand some of the basic mechanics at play before trying to expand on this to be more representative of a real-world situation. To try and understand these basic variables, let's think about a very simple situation, a closed system with a single static source and single sink. We can think about a group of people on an island with some given stock of consumable resources. Modeling the sustainability of this system then is not difficult. We would have a variable for the quantity of stock, some rate at which they are being consumed, and from this can derive how long they will last and thus the sustainability of the system. So these are the most basic elements, understanding the stock, which would correspond to ecosystem services, and the rate of consumption, which would correspond to the input into the economy. This is of course a very simple linear model because the elements in the system are not themselves changing and there is no feedback. One of the first things to add to this model is the fact that the population is changing over time. The rate of growth to a population and its change is typically understood within population ecology with reference to the logistic map, where the rate of population growth is proportional to both the existing population and the amount of available resources, all else being equal. The mathematician Verhulst derived this logistic equation to describe the self-limiting growth of a biological population. By adding this into the dynamic, we get one basic understanding of sustainability in terms of what is called the carrying capacity, where the carrying capacity of a biological species in an environment is the maximum population size of the species that the environment can sustain indefinitely, given the ecosystem services available in that environment. The carrying capacity can be defined as the environment's maximum load to which the population can grow and exist sustainably. To develop a more representative model, we would also have to recognize that the stock, which is the ecosystem, is not just a static variable, but in fact has a generative capacity, the capacity to reconfigure and regenerate itself. So there are really two factors here: the stock of resources, or the ecosystem services, that flow to the economy at any given time, but also there is the system through which these services are generated. This is called natural capital. A functional definition of capital in general is a stock that yields a flow of valuable goods or services into the future. Natural capital is then the stock of natural ecosystem that yields a flow of valuable ecosystems goods or services into the future. For example, a stock of trees or fish provides a flow of new trees or fish, a flow which can be sustained indefinitely. Natural capital may also provide services like recycling waste or water catchment and erosion control. Since the flow of services from ecosystems requires that they function as a whole system, the structure, integrity, and diversity of the system are important components of natural capital. Thus, the supply of ecosystem services can change when we affect the systems that provide them, and as we previously discussed, when talking about regime shifts, these critical ecosystems functions can often change in a nonlinear fashion with tipping points and thresholds. The next important factor to include into our model is that, unlike with the simple island model where resources are consumed and just disappear, in reality economies are dissipative systems. That means during their operation they generate entropy, and this entropy has a degrading effect on the functionality of the ecosystem's natural capital over time. This means we need to think about not just how much the system is consuming, but also, just as importantly, the level of efficiency to the system. Here we're talking about efficiency as a ratio between the total resources consumed and the total entropy exported. The scale of impact that an economy has on the natural environment is attempted to be captured in a model called I equals PAT, which is the lettering of a formula put forward to describe the impact of economic activity on the environment. It posits that economic impact on the environment is equal to P, which is for the total size of population, A, which is for their affluence, representing the average consumption of each person in the population, and T, which is for technology, representing how resource intensive the production of this affluence is. So this goes some way to describing the basic physical mechanisms to the sustainability dynamic. The variables that we've outlined loosely correlate to those used in the first such macro model to global sustainability, which was published in a book called The Limits to Growth in 1972. The original version presented a model based on 5 variables, including world population, industrialization, pollution, food production, and resource depletion. But of course, sustainability is much more than just about technology, demographics, and natural resource supply. Just as important as the basic physical mechanics is a society's capacity to adapt and evolve in response to changes. From this perspective, sustainability is not so much about trying to make everything add up, trying to reduce ecological footprint or make technology more efficient, but instead recognizing that change is an inherent part of the socio-ecological dynamic, and that long-term sustainability is only really going to come through enabling an effective adaptive mechanism within the social system in order for it to evolve in response to changes in the ecosystem and thus endure over time. Adaptation engages both economic, social, and cultural dimensions. On all levels, it requires feedback loops so that people and institutions can receive information and respond to it, seeing the effect of their actions and the state of the environment. On its most basic level, the market economy engineers an adaptive capacity into the pricing system. In general, as a commodity or service becomes more scarce, the price increases, and this acts as a restraint that encourages efficiency, technical innovation, and alternative products. However, this only applies when the product or service falls within the market system. As ecosystem services are often treated as economic externalities, they are often systematically underpriced and therefore overused and degraded. The pricing of ecosystem services, then, is an important part of enabling this feedback loop to function. As long as ecosystem services are externalized, the market has no signal or way of sensing their state, and thus no way of responding and adapting as needed. And this broken economic feedback loop has been a major critique of the free market system and identified as a central cause of current environmental problems on the global scale. But as we previously noted, when talking about the social dilemma, markets have their limitations. They are not effective at dealing with situations that involve some form of commons. Such situations require social capital, the value that is stored in the social bonds that enable effective communications, reciprocity, and coordination. Social capital is central to dealing with the tragedy of the commons problem that otherwise can be very environmentally costly and very inefficient to try and manage through the market. Self-organizing communities that effectively use their social capital become more sustainable, effective, and resilient than those with adaptive mechanisms designed and imposed by external entities. The published literature contains many examples that demonstrate not only the ability of social capital to provide the needed power for the management of community commons property or resources such as water, pasture, forestry, etc., but also to build an adaptive capacity to better tolerate climate variables as well as climate hazards and extreme events. Case studies to the management of sea defense in Vietnam during the 90s, among others, have shown how, in the time of crises, the dormant social capital was rapidly awakened by the community themselves and played an important part in dealing with the change. Social capital enables the community to self-organize from within and use their social capital to build adaptive capacity to be more effective, resilient, and ultimately sustainable, and central to enabling sustainability. Sustainability and adaptation also have a strong cultural dimension to them. Society's capacity to adapt is strongly correlated to how it understands itself, and through this, its relation to the natural environment. People's identity plays a very significant role in their capacity to adapt to change within their natural environment. There is a recognized need to expand understanding of subjective dimensions to recognize the values and lived experiences of people in a place. For example, most investigations into climate adaptation to date have focused on specific technology interventions and socioeconomic aspects of adaptive capacity. New perspectives posit that sociocognitive factors may be as or more important in motivating individuals to take adaptive action. In a recent piece of research conducted in rural Mexico, one of the authors undertook in-depth interviews with a sample of farmers to explore their perception to their social identity in relation to climate risk. These interviews showed robust evidence that social identity mediates between risk perception and adaptation through its influence on motivation. Interviews revealed significant linkages between social identity and interpretation of information, risk perception, and ultimately adaptation. In this module, we've been discussing the idea of sustainability within socio-ecological systems, looking at how this very complex emergent feature of a system is really the product of many different interacting factors on many different levels, making it an inherently interdisciplinary area of study that requires a systems approach for a full analysis. We firstly talked about it on the most basic level of the physical interaction between the economic and ecological domains, identifying the variables involved, such as the supply of ecosystem services, the rate of consumption, and the efficiency of the technology infrastructure. We then went on to recognize the central role of adaptation in enabling sustainability, talking about the adaptive capacity of a society as a function of both economic factors involving well-aligned feedback loops and reduced externalities, but also social factors requiring social capital to enable local self-organizing adaptive resilience. Finally, we noted the role of culture and social identity as another key dimension to the whole dynamic of sustainability within socio-ecological systems.